In school, we're introduced to so many topics, but you're often left wondering when and where we'll actually use them. Today, I can show you how you can use some basic concepts you learn in class 9 and 10 maths to predict the growth of something which is as important as a pandemic, like the COVID. So, we'll start by making a table. So, we'll have the days at one side, and corresponding to each day we'll have the total number of cases. And we know that at the very beginning, at the 0th day, we have just one case. And we'll also add another factor. We'll assume that an average person meets 3 new people every day. So 3 new people. Now at day 1 would have the first person plus the 3 new people he meets. Because the virus spreads by contact. At day 2, we'll have 4 people who already had the infection plus the people they meet, which is 4 into 3, and this is 16. We'll do one more. At day 3, we'll have 16 plus the new people they meet, and this makes it 64. And I think we're all noticing a pattern here. And whenever we see a pattern in maths, we start giving things names. So let's call the days as T and the total number of cases as CT. So CT is the total cases at day T. And now what we see is that CT plus 1, which is total cases at day T plus 1, is the number of people who already were infected, which is CT, plus the number of people they meet, which is CT into 3, because each person meets 3 new people. And this makes it CT plus 1 is just 4 into CT. And now, quickly try to plot this in a graph and see how it looks. So we have the number of days, which is T on the x-axis, and CT on the y-axis. At day 0, the number of cases is 1. At day 1, the number of cases is 4. At day 2, the number of cases is 16. And at day 3, it's 64. So if you try to join these points on the plane we have, it will look something like this. And we have already noticed that 1 is 4 to the power 0, 4 is 4 to the power 1, 16 is 4 to the power 2, and 64 is 4 to the power 3. So we can easily see that c to the power t is nothing but 4 to the power t. And because this dependent thing, this t thing, t is in the exponent, we call the graph which we saw here as an exponential graph. And now one of you might obviously ask that if this keeps on increasing, if it keeps on increasing like this, then where does this stop? Because it can't be possible that it goes on, because we have only so many people in the world. So for this, we'd need to introduce one more variable, n, which is the total population. And one thing we know for sure is that whatever our graphs looks like, it will never go beyond this n, because the number of infected people, the total cases, can't be more than the population. Right. So this is where the probability comes in. So let's just make this box and let this box represent the total population, n. And we know that the portion of this box, which is CT, is the number of total cases, number of infected people, and the remaining portion, which is n minus CT, is the people who are not infected. And among the new people someone meets, that contact turns into an infection only when it falls in this region. What proportion does this region make of the total population? That is just n minus CT by n. So let's go back and see what new cases were in our original equation. So new cases is just the number of cases at day t plus 1 minus the number of cases at day t. which was just 3 into CT from our original equation. And now we saw that out of the total population, n minus CT by n proportion of them were the non-infected people. Initially, we were considering that all the contacts transferred into an infection, but now we know that only those contacts become an infection which belong to non-infected people. So out of this 3 into CT people, we only have this proportion, n minus CT by n of them, becoming a new case. So if we put this new observation into our equation, the equation becomes CT plus 1 is CT plus n minus CT by n into 3 into CT. Now we'll see that how this changes the graph. We had the exponential growth, and we also saw that this graph, this line we are drawing, this curve we are drawing, it would never exceed the n threshold. But now if you see that when this number of infected people, this CT, when it becomes close to n, as the number of days increase, as the entire population starts getting infected, the numerator of this thing slowly becomes 0, and therefore this entire thing becomes 0, and therefore CT plus 1 just becomes CT, or you'd say that no new cases emerge, and therefore at some point we become saturated. The number of total cases becomes saturated, and therefore the initial exponential growth we had, the graph suddenly turns at some point, and then it comes and it stops at n. And this is how a pandemic looks like: exponential first, and this growth, which is exactly the opposite of exponentiation. It looks like it's almost a reflection along this line. This is called logarithmic growth, and this is a naive model of number of cases in a pandemic. And what we saw here, that this basic concepts of logarithm, exponents, and probability, the scientists use some modified version of this to actually model the pandemic.